Okay, it's 11:30, so I guess I'll start our practicum today. So we're gonna do the same style as last time. I'll go through the notebook and then you will have some time to do the answers, and then yeah, we will walk through the solution together. So the practicum today is about knowledge distillation. I believe you have already learned about this in the lectures. So technically, knowledge distillation is improving the performance of some more lightweight neural network using a more powerful network as a teacher. So in particular, today we will look at how to modify the model classes to extract the hidden representation in order to use that for the teacher-student learning process. How to modify the regular training loop in PyTorch in order to include the additional distill loss on top, and how to improve the performance of some lightweight model using a more complex models as a teacher. Yes, so as usual, we will import some necessary libraries. This time, I believe we don't have to install anything. So mostly we will use Torch and Torch Vision for this one. For this notebook, we will use the CIFAR 10 dataset, which is an image dataset for the classification task with 10 classes. And the objective here is to predict one of the following classes for each input image. The image in this data sets are RGB and are 22 by 22 pixel, which means they have 3 channels. And yeah, in total, this is the amount of numbers needed to describe each image. And similar to last time, we will normalize the input by subtracting the mean and divide by the standard deviation for each channel. For this part, you can take the code for granted. Here, the mean and the standard deviation of the data set is already defined. So yeah, this process is already done for you. So this notebook would actually take quite some time to be run on the full data set, even with GPU, which is, I think, not very efficient for the practicum. So in the beginning, you can just use CPU, and then you can limit the data set to however much you want. Here I put 2000. And then here we will take the subset of the original data set just to test whether the code works or not. And later when you go home, or later I will also show you the results as well on the full data set, and then we can discuss over that. But yeah, also you can take this part for granted. The first part of the notebook is to define model classes and utility function. Here we will use 2 different architectures, one for the teacher and one for the model, both of which we're going to use CNN with the same number of filters or kernels. But the teacher architecture, we will give them more like a higher number of layers and higher number of neurons. So this is the code. I would suggest to, well, even though it's provided to you, I would suggest just to take a quick look at it to see how the model is structured. And yeah, so this is the diagram for the 2 models. I think it's quite straightforward, so I guess there's nothing to add here. It's just that in the beginning, before we do the knowledge distillation process, if we just train 2 models individually, then you will see that the loss is only calculated by, compare the probability from the output layer to the goal targets for both models. Here we will define 2 functions to do training and testing. Yeah, it's quite similar to what you have known before. For training, we just loop over the data set and do backpropagation. For testing, we do forward pass on the test split. So yes, this code is pre-given. The first part is to do cross-entropy runs, as in just training the 2 models individually without doing any knowledge distillation. First, we set the seed for reproducibility, define the model, which we wrote the class before already, do training and do testing. This is the deep network, which is the supposedly teacher. And then we do the same for the light network as well to see how they perform individually. And for fair comparison, we will try to initialize the weight of the light models the same way throughout this notebook, because otherwise there would be too many varying factors that affect the performance. Yes, and then we train and test the lightweight network as well. And then we print out the accuracy on the test set. And then comes the interesting part, the knowledge distillation run. So here we will incorporate an additional loss, so-called the distillation loss, into the traditional cross-entropy loss for the student model. For this part, the distillation loss is going to measure how the teacher's output probability distribution different to the students. However, in many cases, the output probability distribution by the teacher is quite, how do I say it, non-smooth, as in it gives very high score to the correct samples and very low probability on the incorrect samples. So they don't contain that much information compared to the original targets anyway. So what we will do is kind of soften the output distribution a bit by scaling the logic with a temperature T. So yes, we just divide the logic by the temperature variable T before we do softmax onto the logic. And here larger T would lead to smoother distributions, thus smaller probability would get a larger boost. The distillation loss is this formula. This is based on the KL divergence. I think this part you have already learned in the lecture. So given the probability distribution P and Q, you have this formulation in the lecture already. And then we just sum them and then scale them according to the sample space size. And then we multiply them to the temperature factor. So I guess there's nothing new here. We would also define two hyperparameters to balance between the two loss, one for the distillation loss and one for the traditional cross-entropy loss. So this is the diagram. The teacher model would already be trained, and now we only use it for teaching the student model. So for the student model, we will still have the normal loss as we had before. But here, in addition, we will also have the distillation loss, which compare between the output of the teacher and the output of the student. So technically that's the idea. And then we will have a method to train with knowledge distillation. And this would be your task where you calculate the teacher logic, student logic, and then you pass them through softmax, calculate the distillation loss according to the formula that I've given above, calculate the normal loss, and then sum them and weight them together. You can play around with the parameters to control the softness of the distribution. So that's all for the first part on knowledge distillation on only the output probability distribution. Any questions so far? Okay. Then
distillation in this case again? Why do we call it distillation loss? Or what happens to the loss there?
I actually don't even know what is the word distill means in English. But technically the idea is that you have a teacher model which have already been trained. Okay. And then you try to use the output of that model as the target to train the student model. Okay. So so we will come to the next part called cosine loss minimization run. So yes, in this section, instead of minimizing the difference in the final output distribution by the two models, as in the output of these two final layers, we will instead try to minimize the hidden state of the student and the teacher instead and try to see if this would help us to gain more knowledge from the student, from the teacher to train the student. So technically, given the two hidden representation vector from the teacher and the student, we can just use the loss function to minimize the difference between the two vectors. And here we will use the cosine embedding loss. Here's the formula, but then in PyTorch, you can just use the predefined loss, which is somewhere in the code given to you already. So not much worries about that. It's just one thing to keep in mind that the hidden dimension size of the teacher model would be larger than that of the student model because they contained more neurons per layer. So we would have to include an we would have to include an average pooling layer so that we can match the teacher hidden representation size into the student hidden representation size. That's the idea. So for this section, you will also use the same class with some modification. And your task here is to flatten the output by the models and then do pooling to match the hidden dimension of the teacher to that of students, and then return that in addition to the logic itself. And for the student model, you also need to return the flattened hidden representation to be calculated later. And next we would, here's some code for you to do sanity check on the size of the hidden representations vectors. And this is the diagram of how the method worked this time. So as you can see, still we have the normal loss, but instead of adding the distillation loss by comparing the output of the two models, instead we would be comparing the flattened hidden representation inside of the model, and hopefully it will give us more information than just the final output distribution. And here we have to do some changes in the training process, where you should extract the hidden representation from the teacher, from the student, calculate the loss using the cosine embedding loss, calculate the normal loss, and then weighted them, do the weight sum on them the same way as you did before. And then we would do more testing on that. So that is all for the second part. Any question on this? Yes.
How do we know how the weights are between the two losses? Is that learned too?
No, that's not learned. It's like a hyperparameters, which you would have to like test out of it. I think there's some default value in here already, so you can just try with that one first and then change it according to, I don't know, your feeling. Okay, the last part is to do an intermediate regressor run. So the minimization of the two hidden representation that I just told you is quite naive, because when the two, well, it can happen that the teacher model is bigger, so it learns the hidden representation in a different way compared to the student. So it might not always make sense to pull them to be exactly the same the way we did. And another thing is that, as written here, cosine similarity works better than some other type of distance for vector of higher dimensionality. But here the dimensionality of the vector is 1024, which is still very large. So it might be difficult to extract meaningful similarity just by cosine similarity. So in this section, instead of trying to push those two vectors to be close to each other, we would instead include like a network regressor, like a trainable module, in order to map those two vectors together. And hopefully it will give us better performance than the approaches before. This part I already mentioned. Yes, so technically this is the idea. So as you can see here, again, normal loss, and then we try to map these two vectors. But here, instead of using cosine similarity directly between these two orange representation, we would add another trainable module in between to map the two representations. So again, we will do some modification onto the normal class definition. And your work here is to extract the feature map, pass the input through the regressor as in the new module that we defined for the mapping, and do the same for the student as well. And again, we have to modify the training loop where we need to extract the feature map from the teacher, the same from the student, and then calculate the hidden representation loss. Here we would use mean squared error because the two vectors now is exactly the same, so we can just use mean squared error for the distillation loss. And again, calculate the normal loss and weight them together and do back propagation. And then in the end, we will have a block of code where we just compare the difference in performance of different methods. So I guess that's all. So if you have any question, you can ask.
How does it the transfer of the way of deciding of the weights from the teacher network to the student network from layer to layer work again? Because what I understood, it's like that we have you look at the representation of this of the teacher network and try to put that information also in the weights for the corresponding layer of the student network or something. And how does it work again?
Yes, so
because I think this is what you in this last step that you explained, we take another step for this, right? We try to regress it somehow, but how does the normal way work again, and how do we change that in that step?
So I'm not particularly sure what is the normal way in this case, but I think what you're referring to is the most similar to the second section in the practicum, where we just try to maximize the similarity between the hidden representation of the teacher and the student of these two corresponding layers.
And how can we measure the similarity?
We can, yeah.
I mean, are they of the same type of layer, for example, or?
Yes, they are the same type of layer, just different in dimension.
Okay.
So here we would use the cosine similarity, so just to maximize the similarity between the two vectors. But it's problematic because the teacher vector is bigger than the student vector.
Yeah.
So there's this pooling step in between.
Okay. So we have like a matrix of weights, and somewhere in the left upper corner, there's really high values, and they will get pooled to one really high value because the dimensions are reducing, and then because of the cosine loss, we try to get in the student network in the corresponding matrix of weights also really high value in the left upper corner, something like that.
But I wouldn't comment on it as in trying to pull the weight of the students closer to the teachers, because, well, they are different set of weights. Like the teacher have a much larger set of weights than the student. Yeah. So here we're just trying to make the student output the same thing as the teacher. So it's not pulling the weight together, but it's more like pulling the output of the two models closer together.
But if we like the thing with the output, aren't we doing that after? Like because in the visual graphics here, we see some connection between two layers and not between the output of those two models.
Yeah, I mean the output of the layer in this case.
Okay.
Okay. Yeah.
And for what input? For any input or?
Yeah, so yeah, we do the same for every input. It's in every training step we do this.
Okay.
Okay.
Thank you.
Any other question before you start working on it? You can also ask question in between while you're looking at it as well, so no rush. Okay. Okay, your first task on knowledge distillation run is to fill in the training loop. So here for the teacher logic, you would have to do tosh.nograph because your teacher model is already trained, so you wouldn't want to modify your model network, but you just want to get out the logic. So and then for student logic, you also pass the input through the student model. This is where you calculate the soft and log probability of the teacher, where you first divide the logic by the temperature parameters as we discussed before, and then pass it through log softmax, and then do the same for the student. And then come to the part of calculating the distillation loss. So this is just the formula that we have seen before written out. So because this is log probability, we can do subtraction instead of like log and then division like we've seen before. In theory, it's the same thing. And then we calculate the actual loss from the main classification task. Then we calculate this weighted sum of the two loss depending on your predefined two weights. So that is the first task. Your second task is on the cosine loss minimization run, which is where you try to minimize the difference between the hidden representation of the teacher and that of the model. So here you have to flatten the convolution output. And then for the teacher, you have to do a pooling step so that you can get to the same shape of that of the student. And then you repeat it, you return it along with the logic from the teacher. For the student, you don't, the shape can be kept the same. So you just have to flatten the output and then also return it along with the logic. Your next task is in, which part is it? Okay, still in the cosine minimization run. No, this part is for the hidden representation. Yes. So in the training loop, you have to again extract the hidden representation, and you can ignore the logic because now we will not use it to teach our model anymore. Then you can calculate, same thing for the student. You also extract the logic and also the hidden representation. And then you calculate the hidden representation loss as in our new distillation loss by calculating the cosine loss between the hidden representation of the student and that of the teacher. And then we will set the target to be the vector of 1 because 1 would mean the perfect match between the two hidden representation. Then again, calculate the standard main task loss and then weight them together using your two hyperparameters. And your last task is to fill in the blank for the method where we add the reversal module in between to map the two hidden representation of the teacher and the student. And here you just have to extract the feature from the teacher and return it along with the logic. For the student, we would include an extra regressor. And here we just use another convolution layer that map it to the same dimension. And then in the forward function, beside the logic, we also have to return the regressor output to calculate the mean squared error later on. So here you also modify your training loop So again, for the teacher, you try not to modify the weight, but you just only want to extract the feature map. Do the same for the student. And then we calculate the mean square error loss between the regressor from the student, from the student and that from the teacher. And then same thing, calculate the main task loss. And then weight the two loss together using your predefined weighting balancing hyperparameter. So I guess that's all the tasks unless I missed something. So does anyone have any questions? If there's no question, I guess we can close the session, and you can also, again, write me on Ilias if you come up with any question later on. So thank you.